Hey everybody, today I'm going to be looking at solving a problem that happened with my little shoe mount Doomo light meter. I broke the foot on it, and this is, the foot was made out of plastic, and so it's kind of predictable that depending on how you use it, you're going to end up breaking the foot on it. So in this video, I get to combine two things I really like, which is film photography and machine shop work. So we're going to go and take this broken foot off and reverse engineer it and make a new one out of metal. And at the end of the day, we're going to have a much better part. Let me show you why I have two of these and why the foot ended up breaking. First thing is, this is a rangefinder camera with a cold shoe in the center, and this has the foot in the center. This is the Voigtlander, and I put it on here, and there we go. If I had this off to the side, which you can do, there's other mounting holes in there. If I had it off to the side, it would get in the way of the shutter speed dial, or it would get in the way of the rewind knob. So I have to have a second one, because with my twin lens reflex cameras, you have this problem, which is there's the cold shoe right there. If you have the light meter with the shoe in the center and you try to put it here, it's going to run into the strap lugs and it's not going to fit. So you have to put it on the far edge like this one, and it slides into position just like that. But you can see that if I can get the light just right here, you can see that there's nothing supporting the bottom of this. And if this heavy camera, and this camera weighs close to 3.5 pounds, if this is sitting in a camera bag and hits something, the force against this bottom edge is going to tend to break something. And that something is probably going to be the plastic foot on the base. Let's take a closer look at the problem, and then let's get into fixing it. So here we go. This is the patient, and we take it out of its little case, and you'll see that, yes indeed, the plastic foot is broken, and it was probably not too much pressure it took to break that with the way I had it mounted on the side of the twin lens reflex camera. So we're going to just take the Voigtlander, this is the other light meter I have, and we're going to copy its nice metal foot, and we're going to use the dimensions off of that, with the singular exception of the screw positions, because notice this one has 3 and the other one had 2. But notice how Voigtlander did us a solid, made a good metal foot instead of the cheaper Doomo, which has the plastic foot. Definitely a difference in quality. And that goes all the way through with this Voigtlander light meter. It is much better quality, but is it $100 better quality? I don't think so. It's still a really nice light meter. So we need to figure out the position of those screw holes, and you could eyeball it or something like that. But for machining a part, we want to get a precise measurement. Here's the foot off of the Voigtlander, and you see I was able to measure using calipers and get all the dimensions of the size and the wings and the base cuts, everything like that. Only thing that's different, of course, is the screw holes. So what I did is I put the original screws back in the part, and we're going to measure these. We have to figure side to side and top to bottom, center to center measurements. Now the way you do that in machining, if you have 2 pins, is you measure the outer dimension and you subtract the width of 1 pin. So we're going to do that, and I have to hold these calipers really square to the part, and this feels fiddly and seems janky, but it actually worked out surprisingly well. We're going to use a second method to do the same thing using a height gauge, and much more accurate, and we'll see how close we got. So you can see the measurement, 380, about right there. And then we figure the width of 1 pin, or 1 screw head in this case. And we're going to subtract that 1 single width from the outer dimension we just measured. And that will give us center to center distance in 1 direction. And so here we go. We ended up with 380 on the outside. And we've got our width of the screw, 157 thousandths, and we do the math. And, drum roll please, 223 thousandths. That's our center distance in that direction. And we have to do the same thing the vertical direction. I'll spare you the actual measuring. And you see we've got the same thing going on here. Subtract one screw width, and we have 319 thousandths in that direction. Now let's do the same thing on the surface plate. So now we're going to use a height gauge on the surface plate. And this should give us a much more accurate measurement. We take the part and we put it on the edge of the surface plate. We've got to hang it off there because the dials get in the way. And then we take the nose of the height gauge, run it down the part, leaving a nice little gouge in the paint on the brass base. Nothing a Sharpie can't fix. And measure the height of the top of that screw and read the dial. And we see the bottom scale shows 3 and then the dial shows 65. So that's 365 thousandths. When we do all the math, you'll notice that we got 320 and 222 for the center distances. And here's the janky way, 319 and 223. We were 1,000th off using the janky way with the calipers. So I guess I'm just going to use the calipers. Now this is a piece of German silver. German silver is brass with nickel in it. And it looks nice and it wears well, but it's terrible stuff to machine. It's gummy, it sticks to the tools, leaves burrs. But I've got this left over from another project and I'm going to use it. And this is actually what I made before. This is from a steam engine, and these curved parts, I made them from German silver, and you can imagine that that was an interesting problem doing all that rotary table work to make these curved parts. Let's just chop a slice of this metal off, and we're going to use that to make our part. First, we're going to use the parallels to set it up in the vise like you typically do. Problem is the two parallels are too thick. Normally you would use a pair of parallels, but they're too thick for the part, so I'm going to only use one. Except when you use a single parallel, it can tilt in the vise, and I don't want it to do that. I want it to be held firmly in position so that it holds the part at the right level. So I'm going to use another machinist tool called a flexible parallel. And this is just a piece of spring steel, and I'm just going to use one, and it's shorter than the fixed parallel, and that's going to force the parallel to the back of the vise jaw. And there we go. Now we have the part held firmly in position on what I'm hoping will be its flattest face. The goal right now is just to square the material up. I don't know what kind of cutting material you're supposed to use on German silver, but I use WD-40, which is what you typically use on aluminum, which is a similar sticky material. And I like it because it makes these little streamers as the chips fly off. It's kind of cool to watch. So we take a few passes here, flatten the one side, and then we're going to flip the part over and flatten the other. And we got to file things down because the burrs that materials like this make. And so now we cut the other side, and we've got two parallel sides. We can't just flip it to the third side because we'll end up with a parallelogram. We need to put it in the vise sideways like this and use the side of the cutter to give us a proper perpendicular cut. But if I clamp it on the right side of the vise jaw is going to twist because of no counterbalancing force on the left side. We use another cool machinist tool called an adjustable parallel. See how those pieces slide past each other? It allows you to get a very precise width. And so, see, I get it in there and set it to the same width as the part, cinch that screw down, and now I have a piece of metal that's the same size to counterbalance the force. Loosen the vise, drop the parallel onto the table, leave a nick in the middle of the machine table, put it back, put the two pieces of metal at the opposite ends of the vise, tighten things down, and now you can see that the forces on the vise are balanced and the jaw is not going to twist. Now we can take that cut off of the right side and guarantee that we have a nice square 90-degree angle on that end. And we'll just flip it around and make another cut, and we have a nice squared up part. Now we need to measure all of these dimensions and find out how much meat we need to take off to bring it to size. If you see a machinist with rolling papers like this, it doesn't mean they're making funny cigarettes. It means they're positioning their tooling. I've written down the current dimension in thousandths of an inch and the desired dimension in thousandths of an inch on that piece of paper that's sitting on the vise. And I'm just going to take small cuts, about 10 thousandths a pass, with this cutter while watching the digits of the display on the right side, and we'll sneak up on the final dimension and get it in perfect. I guess I could just do this on a belt sander. It's not a big deal. Here you can see what I'm doing. For each pass, I'm adjusting that height, which is the bottom number. You see it says 710 thousandths. Well, it moved, but 710 thousandths. So then I use the X dimension as I'm running the table back and forth, take a cut, and then I'm going to adjust the height again. You see, now I'm down to 698 thousandths. I really went down to 700. Taking 10 thousandths off a pass. Again, it's not a big deal. I'm not in a rush, and I don't want to have a funky looking finish. Go back and forth, and there it is. The part is the perfect size in the width and the length. The thickness is still not to size. You can see it's a big chunky looking piece of metal right now, too thick. But in the blink of an eye, we will machine the part to thickness. And there I am observing the beauty of the tool marks, which will be ruined when we make the other cuts on the part. We have to cut these wings, and then there's going to be a little valley in the middle. So here I am cutting the wings. And you can see I've got clamped in the vise, and I'm just going down and back and down and back and down and back, little by little as I make the cuts. And then we flip it over and do the same thing on the other side. And eventually, we'll have both wings done. And there it is. What's left is cutting that little valley in the middle and then drilling the holes. And I'm going to spare you both of those operations as we cut right to the finishing of the drilling. And there it is. The valley has been cut, the two holes cut, and counterbored. The part is done. Now we just need to file it and do a lot of sanding. And I just went up to the belt sander to make that flatten the corner. No need to do that in a fancy machinist way. And you can see from the blackened fingers the work I was doing. I filed little on-ramps onto the wings so they slide into the shoe nicely, and rounded all the corners off. And here we go. The new metal foot is in place on the Doomo light meter. So that's it. This part is now solid and fixed. It will last quite a long time as long as I don't abuse it. And I had an enjoyable time doing the work. It took about, maybe an hour and a half, just because I was moving the camera around stuff to catch it. Otherwise, that's probably about half hour to maybe an hour of machine shop work. It was a fun little project, and hope you enjoyed it. Now, thank you for watching. Go out and shoot a roll. Have a nice day.